Hello, everyone. This is the last topic of the semester, fluid. So now we are really jumping out of E&M and starting to talk about new area of physics. So what's a fluid? Fluid is, so usually you will hear about three phases in life: solid, fluid, and gas. So solid means the particles, they have interactions between them, and that bonding is so strong that the particle cannot really move. But fluid, on another case, on the other hand, the fluid has some interaction, but it can freely move around. It's kind of fluid. But the gas, it means the particles, they just pretend they don't know each other, like they have no interaction, they just freely move in the air. So today we are going to talk about the fluid, which is the phase in the middle. So fluid in the physics about fluid can be very, very different from one particle. So say if you understand what's the physics of one of the particles in this fluid, you still have no idea about what's this entire fluid look like. So this all come back to this line: more is different. The more is different is one of the most famous line in physics in physics in the last decade. Basically, the idea is saying people, the physicists, we usually think if we understand one particle, then we understand the whole world, because the world is composed of particles. But now, gradually, people started to realize this is not really the case, because even though we understand one particle, we still don't understand what's happening in a billion particles, because we cannot draw free body diagram for billions of them and study their interaction. This is just impossible, theoretically. So to study any object which is composed of like millions, billions of particles, a lot of them, we kind of need a new way to think about this problem. And fluid is one of such a topic. So today I want to focus on some very interesting or big physics quantities that you will hear about fluid in life. There's a lot more we can talk about, but I just want to focus on the most two simple and common ideas. So, oh, and by the way, today everything I'm talking about today is about fluid at rest. So we call it fluid statics. The fluid are not moving at all in all the lectures I'm talking about. I'm talking today. So if you were a mermaid, so imagine that you're swimming under the sea. How do you feel? Like if I want you to come up with a physics quantity to describe your feeling, how would you feel that? So say if you dive deeper, how do you feel? You will probably feel a lot of pressure. Okay? So you will think you probably have heard people saying like, oh, a diver will feel more pressure under the sea. So instead of saying they feel more force, they would say they feel more pressure. So pressure is the physics quantity that we will use to describe force in the fluid. So pressure, that's our first physics quantity. So what is a pressure? So by definition, when you are under the water, we don't really talk about force at all, because force can come from everywhere. So instead of force, we will talk about pressure. So pressure by that definition is the force in a unit area. So this is my pressure. Pressure is basically, you can think about if I use a 10 Newton to push on this object. This object are going to feel a force. That force is called 10 Newton. But if I just look at this cross section, each individual unit area, okay, this area here, this area, like per unit area, like 1 meter square, like per unit area, it's gonna feel a pressure. So for example, this is 1 unit area. This guy will feel a force, and that force is the pressure. So basically, pressure is force divided by that area. And here you wanna pay attention to this. Force is the force that we only account for the force which is perpendicular to the area. So for example, if I have an object here and I'm trying to use 10 newtons to push this object to the right, but my plot looks like this. Okay. So now you can see this guy is not pushing anything, right? It's just it's in parallel with that surface. So in this case, there's no pressure at all because it's not even pressing it. Okay. So when we count the pressure, we only count the force which is in perpendicular with the area. The unit for pressure is Pascal. We call it PA. This is the SI unit. 1 Pascal is 1 Newton per meter square. It's a derived quantities. Other common units that you will see, which is not SI unit, including like atmosphere, ATM, or 1 atmosphere is 10 to the 5th Pascal. For example, the milliliter mercury. This is also a very commonly used pressure unit. Something like this. Okay. So now let me give you an example. So think about this case. If I use a force, like as a finger, to poke this balloon, compared to I use the same amount of force, but I use a needle to poke the balloon, which balloon is gonna pop? Which one has higher pressure? So you probably already know the answer. The answer is for the right one, because the right one feels a higher pressure, so it will pop first. So how do we apply this idea of pressure in fluid? So first, we need to know how you feel when you're underwater. So say if you was a point charge. So if you was a point charge here, and you're swimming, you will feel like the water is pressing, is like squeezing you, right? So you will feel the pressure from everywhere, from all directions. And so now remember here, I'm assuming this particle is so small, the size is very, very small. Okay. Just imagine it's like a dot. So the pressure, you will feel the pressure all around you, and all these pressures are gonna be the same. They have to be the same. Because if they are not the same, for example, say if this pressure is higher, then this pressure is gonna push this object downward, right? So this pressure has to be the same as the pressure coming from the opposite direction, so that they will cancel out. Eventually this particle can stay there and not moving. So basically in fluid statics, everything is in equilibrium, they're not moving. So the pressure in all directions should be the same. So this is our first concept here. Pressure exerting on the object in the fluid is applied in all directions, and they are all the same. Okay, so now, now we know the idea of pressure, it is from all directions. Let's think about this. Why would I compare the pressure at the X point and the Y point? As we said, like if you're deeper in the sea, we usually feel more pressure, right? But exactly by how much? So that's the question we want to study here. So to study this, the tools we have is the free body diagram. So I'm gonna borrow the free body diagram to solve this problem. So to do the free body diagram, I need an object. So I'm gonna say single out this column of the water. So I'm gonna focus on this, and this is going to be my object. So, and based on this object, I can draw a free body diagram of this water column for this guy. So this guy, you can see that this guy first, it will feel a pressure coming below. And we know P equals to F over A. So which means from the bottom, this object are going to feel a force that is the pressure pressing at it times the area. So that's the first force pushing. So this force will want to push this entire object upward. All right. And on the top, we also have the pressure from the air pushing it downward. So this pressure from the air will want to push it downward. And again, if the pressure of the air is P naught, so assuming the pressure at this point is P0, the pressure at this point is P. Then this air will also give this object a force, which is P naught times A. On the side, we'll also feel, this column will also feel the pressure pushing from both sides. But this side, you can see it's symmetric, so these two forces are going to cancel out. And eventually, on this water column will also feel a gravitational force. So we will have one more force. So you can see these four black arrows that indicate the pressure, the force coming from the water and the air. But the red arrows indicates that the gravitational force coming from this column. So now we can add this up. This is a two-dimensional free body diagram. We add up the x component and the y component. The x component are going to cancel out. These two are going to cancel out. And these two will cancel out. Eventually, since we have studied the case that the fluid is not moving, so all the force must be balanced. So we know these two are the same. This one and this two will be the same. So let's write down all of, analyze this free body diagram in x and y component. X component, we say it's 0, and the y component, we have PA, which is the upward, equals to downward, P naught A plus mg. So let's massage this a little bit. What is mg? M is the mass, right? And we know mass is nothing but the density times the volume, because density is mass over volume. So m is rho v. All right, so then we come to this equation. And now we can divide this equation by A on both sides. So then we will come to this relation, P equals to P naught plus rho GH. Because volume is the area times the height. So when you take a volume divided by area, you will get the height. So this is the first equation, the first relation I want to introduce you for the pressure. In the pressure, we usually don't know exactly what the pressure looks like at a certain point until I'm giving you some information from experiments. But what we know is the pressure difference between any 2 points in the water. So say this water and this point and this point, this pressure will be higher than this pressure. And higher by how much? By rho, which is the density of the water, times g. G is 9.8. This is the gravitational acceleration. And the h is this height. So basically, this point A oh sorry, this point P, this pressure is higher than P naught by this amount of the water weight. This is another concept which is very which is the same as this equation, but it's very counterintuitive. So I want to single out this concept and tell you this. The change in pressure applied to an enclosed fluid is transmitted undiminished to all portions of the fluid and to the walls of its container. So what does this mean? So this means, it basically means the same thing as this equation. So for example, let's say this is 2 Pascal. This point is 1 Pascal, which means whatever water it is here, only put 1 more Pascal, like on this X point. So this guy would be 1 Pascal plus 1 Pascal, which is 2. That makes sense. And now say I put another, like a mass object. I put this mass object on the water. Then this mass object will push down this water, will push this water down, right? So this mass object is going to give this Y point some pressure. So I'm gonna say maybe this mass object is giving this pressure, like say 5 Pascal. So if this mass is pushing this Y, so give this Y and another 5 Pascal, how does that gonna affect my X point? So this X point, based on this equation, we know this X point is basically whatever pressure it is at Y, which is 5 now, plus the difference in between, which is 1. So the pressure down here will be 6 Pascal. So that's the meaning of this one. A change in the pressure, which is like a 1 Pascal to 5 Pascal in this case, this pressure will apply to all portions of fluid. Every point, single molecules in this fluid, even though they're not directly in contact with this mass object, they will still feel that pressure, which is described by this equation. And in the following, I'm gonna give you a few examples, and you can see. Now you probably feel like you kind of understand it, but maybe not fully. I'm gonna ask you a few questions so that you can slowly digest that concept.